In this video, we're going to learn about light behaving as particles. Now, previously, we've understood that light behaves as waves, and that was understood by scientists for a very long time. The conclusion that light also has a particulate nature, that it behaves as particles, that was something that's actually more of a recent discovery. And it was discovered through the photoelectric effect, which states that if light has enough energy, it can knock electrons off the surface of a metal. So essentially, metals, they're atoms, and atoms contain electrons and nuclei, positive nuclei, negative electrons. There's attraction between them, and it is possible to overcome that attraction by adding enough energy to the electron to cause it to be ejected. Similarly, we are attracted to Earth, but if you jump very, very high, you can overcome Earth's gravitational pull. Now, if we look here, this is a red light, and it's shining on a metal surface, and we don't see any electrons being emitted. I'll point out that this is a very intense red light. It's very bright, and yet no electrons are being emitted. So, question is, what will cause the electrons to be emitted? If we turn up the intensity of the light and make it ultra bright, it still will not work. What will work? Well, we'll change it to a blue light, and we can see that the same intensity of a blue light causes a lot of electrons to be emitted from the surface of the metal. But what's interesting is that even a low intensity blue light will still cause electrons to be emitted, just maybe not as rapidly as with a more intense blue light, but still, at least you're getting some emission. In the case of the red light, there was no emission of electrons at all, regardless of intensity. So this helped scientists understand that light exists as individual particles that are called photons, and the energy of each photon really is independent of how intense or bright the light is. What matters for the energy is the frequency or the wavelength of light. So, if we look back here at the blue light apparently is sufficient for, in terms of energy, it's sufficient for causing electrons to be ejected from this particular surface. And a more intense light just means more photons are being released per second, so you get a faster rate of electron emission. But again, even the most intense bright light, the most intense red light in the world apparently would not cause electrons to be emitted from the surface. Wavelength is what matters. Frequency is what matters. The color of the light is what matters, not how bright it is. So the equation relating the energy of light to its frequency or its wavelength is shown here. Frequency, this is measured in hertz. Hertz are also known as inverse seconds, or that can be shown as seconds to the negative first power, or 1/seconds. Those are all the same thing as hertz. The wavelength needs to be expressed in meters because c, the speed of light, typically we use 3.0 times 10 to the 8th meters per second. We can round it to 3.00 times 10 to the 8th with that many sig figs. And note this is in meters per second, so we will need to have wavelength that's expressed in meters. So how can we put this together in a problem? Well, let's take a look at this one right here. We know that a lithium atom very easily will lose its outermost electron. All it needs is 8.64 times 10 to the negative 22nd joules of energy. So we've got to decide whether this blue light with a wavelength of 465 nanometers will have enough energy to ionize the lithium atom. So what we need to do is use that formula, E equals hc over lambda. lambda being wavelength. We also know that E is equal to h nu, nu being that thing that looks like a V, but that would be frequency, would be nu, and we don't have frequency here. So we can write in this being equal to Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. Weird unit, I know. And we're going to multiply that by 3.00 times 10 to the 8th meters per second. And we're going to divide that by the wavelength. Now, the wavelength is 465 nanometers, but because that's in nanometers and we have speed of light in meters per second, we also need to take the 465 nanometers and multiply by 1 meter over 10 to the 9th nanometers. And what we will get is 4.65 times 10 to the negative 7th meters. The nanometers cancel, and we get meters. So we need 4.65 times 10 to the negative 7th meters. Now note, the meters and the meters cancel, the seconds and the inverse seconds cancel, and the final unit that's left is joules, which is energy. Energy is equal to a certain number of joules. So I know that I'm doing this problem correctly. If I multiply Planck's constant times 3.00 times 10 to the 8th divided by this wavelength, I'm going to get 4.27 times 10 to the negative 19th joules. So what we're saying here is that this is the number of joules per photon, and I can even write that in here. Every photon has that much energy, but every electron only needs 4.64 times 10 to the negative 22nd, 8.64 times 10 to the negative 22nd joules of energy in order to be ionized. Because this value that we've calculated as the energy for the photon, because that is so much greater than the energy required to ionize, we could say, yes, blue light at 465 nanometers can ionize lithium. Sorry, my stylus is very laggy today, but hope this video has been helpful, and let me know if you have any questions or comments in the comments section. Thank you.